Hello everyone, welcome to another video of Miss Wallace Teaches Chemistry. In this video I'll be looking at polymers, and this is at the grade 11 CSEC level. If you're doing polymers, this video is also for you. In this video I'll also be looking at addition polymerization and condensation polymerization. Now these were just the objectives. We're also going to work out the monomer of different given polymers. We're going to look at the different polymer linkages, knowing the difference between the ester linkage, the ether linkage, and how protein is formed. We're also going to state the uses of different polymers, specifically the addition polymers and the condensation polymers. In the end of course, I'll be looking at some past paper questions that have been out by CXC, and we're going to look at how to answer them. Now, first thing is, when you think about the word macromolecules, macro usually means something large. And I know you've seen this word before in biology, right? Now, macromolecules, they're formed by polymerization reactions. And as I said earlier, we have two types of polymerization. We have condensation polymerization and addition polymerization. For condensation, this diagram does not have it, but condensation polymerization can include both naturally occurring polymers and synthetic polymers. And the main naturally occurring ones are like the carbohydrates, the proteins, and the nucleotides, which are formed by the glucose, amino acids, and followed by our nucleic acid. Now for the synthetic polymers, under condensation polymerization, it could be polyester or polyamides. Those are just some examples. Now we go over to the other side for addition polymerization. We're really thinking about synthetic polymers, so like the polyalkenes. Those are plastics. All the plastic bags that you have been using, those are your polyalkenes. And this is saying thermoplastics, thermosetting plastics, those are all addition polymerization that involve different types of alkenes. Now note that sometimes these alkenes can have different subgroups on them. That's what makes the different plastics have different properties. Now continuing to macromolecules, as I said earlier, macromolecules are large molecules of different, they're made up of different smaller repeating units. So these molecules have smaller repeating units that are joined together to make the large macromolecule. So an example, I believe you would have done this in grade 9, right? An example being the carbon in diamond. As we know, carbon in diamond has a tetrahedral structure. It's joined to 4 other carbon atoms, right? So this carbon here being the central atom joined to 4 other carbon atoms, and it just, the structure continues and continues and continues. And that's what macromolecules are. They're very similar. They're just joined by different repeating units forming one combined structure, right? Another example would be molecules. So we said atoms such as carbon in diamond, and another example would be molecules such as ethene in polyethene. Now once again, macromolecules, they are large molecules that are formed by the polymerization reaction that have different, or that has repeating monomer subunits. Now for these macromolecules, they have subunits that are formed from covalent bonds to make a polymer. An example, proteins, which are made by amino acids. So amino acids, you have thousands of amino acids being joined together. Note the word amino acid is made from an amino group and an acid attached to it, right? This acid part here, combined with a lot of different amino acids to give you protein. Then you also have lipids, which are made of thousands of fatty acids combined together. Also carbohydrates, you know, carbohydrates are made up of monosaccharides such as glucose and galactose and also fructose, all of those combining to make carbohydrates, right? Then you also have nucleotides, which are made up of nucleobases. Now note that these at the top here, these are our macromolecules, and these at the bottom would be the monomer, which combines with other monomers to give us our macromolecules. And we're going to get at the definition just about now for our definition of polymers, right? Now note that macromolecules, they are examples of polymers. Now polymers, they are large molecules which are made up of thousands of repeating small molecules known as monomers bonded together. Once again, for the simple definition, polymers are made from repeating units of monomers bonded together. So I'm just going to highlight the definition that you need to remember. Are large molecules made from many repeating small molecules. You don't even have to say the molecules, but many repeating small monomers bonded together. That's polymers. So polymers, once again, they are large molecules made up of repeating units of monomers bonded together. Simple. Right? A polymer is a substance. I have substance repeating, but follow along. A polymer is a substance made up of large molecules, each molecule containing 50 to 1 million simple repeating units. Polymers equal repeating units joined together. This definition right here could also be a simple definition. Just make it into a sentence. Polymer definition. Now, as we know, as I would have said earlier, some polymers can be natural, right? Natural, made in nature, such as the polymers found in our bodies, like protein, for example. Then you have the man-made polymers, such as plastics. And let me tell you, the man-made polymers are quite dangerous, which we will be getting into. Right now, just to repeat our definition before we move on, a polymer is a macromolecule formed by linking together 50 or more monomers, usually in chains. So this slide here has about 3 different definitions that you can actually take off and choose to remember. As long as you have repeating units in your definition, you're good to go. Right now, look at it here. This image is a prime example of how it looks. So this right here could be thousands of monomers. Then polymerization happens, where we join our monomers together to make the polymer. That's how it looks. That's it. Now, a monomer versus a polymer. Monomer versus a polymer. When macromolecules are made of repeating molecular units, these small units are called monomers. So the repeating units, the small units, like we could say like the base unit, for example, the repeating unit is the monomer, right? A polymer, on the other hand, is the macromolecule that is made up of monomers, right? So the monomer is the repeating unit, but the polymer contains thousands of those repeating units. That would be our difference. Right now, looking at it here, this is our polymer. It contains a lot of different repeating units, while the monomer would be the repeating unit itself. That would be our monomer. Right now that this says polymers can be made from one or more types of monomers. Right, and that is quite true. You can have, especially in your condensation polymerization, you can have different types of repeating units coming together to give you a special type of polymer. And that's actually how the body works, because things that occur naturally are quite beautiful in a sense that they are very random. They're very, very, very random. Yes, it's selective, but it's random. And because it's so random, you have different things forming naturally, right? That's how DNA is even made. You have different types of amino acids coming together. I believe there are 20 different types. Don't quote me on that. But I believe there are 20 different types coming together to give you your DNA, or coming together to just give you a particular protein. Alright, now some examples of polymers. You have Teflon. Teflon is a good example. So like some non-stick pans, that's Teflon, that's a polymer. Rubber is also a polymer. Plastics are polymers. The polyester jacket, made from a lot of different esters coming together to give you the polyester. There's also sugarcane. Sugarcane is an example of polymers. You know that sugarcane has a lot of different, not different, but it being sweet, it has sucrose. And you know that sucrose would have actually, you have to make sucrose by joining thousands of monomers of glucose to give you the actual sucrose. There's also DNA, RNA, and wool that is found on sheep. The types of polymers, you have natural polymers found in nature, example carbohydrates, protein, and DNA, and synthetic polymers made in labs, example nylon and polyethene. Same nylon that they use to sew, that's the same nylon. And we could also talk about polyester, right? Those are all quote-unquote plastic, right? These are just some more examples. I believe we would have looked at most of these, but let me see which one we did not look at. Epoxy, that's just another example of synthetic polymers. Note, rubbers are natural polymers. They are found naturally in nature. Anything made by a living organism would be somewhat, or would be considered as a natural polymer, but if it is man-made, that would make it a synthetic polymer. Now for polymerization, it's a process of forming polymers from monomers, and it can happen naturally and artificially, which we say synthetically, that's the word. And there are 2 types of methods for polymerization. We have addition polymerization and condensation polymerization. We're going to first look at addition polymerization. And alright, now looking at this, I know you must be curious, how do we go from a monomer such as tetrafluoroethylene? Let me just highlight it. So we go from a monomer, this would be our monomer here, the repeating unit per se. And yes, it's an alkene. It has a double bond between the carbons, so it has to be an alkene, right? We have this as our repeating unit, the monomer, and then we somehow form this. Thousands of monomers coming together, known as polymerization, right? Now, looking at it, on the monomer side, we would have had our double bond, and when we go to the polymer section over this side, we can see that there are no more double bonds present, right? And that's what addition polymerization is about. The fact that we have a double bond present, we're able to break that double bond so that we can accommodate even more bonds, right? It's very similar to when we would have done addition reactions of alkenes. So in the polymerization reaction, we continue to add polymers to where the existing double bond was until we we add monomers until we make our polymer, right? Now continuing, addition polymerization takes place when small molecules join together and the polymer contains all the atoms in the monomers. Usually this involves monomer containing a C double bond alkenes. That's for addition polymerization. Addition polymers are made from alkenes, which is a C double bond C, as I would have said earlier. Double bond breaks and monomers join via single covalent bonds, right? So these are our covalent bonds. The resulting polymer contains all the atoms from the original monomers. So we don't lose any atoms. We don't substitute. It's not substitution. We don't substitute any atoms. We're not losing anything. Instead, all we're doing is that we're breaking a double bond and we're simply just adding something to where that double bond would have been, right? So looking at this example here, this is our double bond. This is an alkene. This would have been ethene. Break this double bond. When we break this double bond, note that it would have just been, I'm just going to draw what we have here. This is what we are going to have now. Right, that's what we have now. Note that, remember that carbon is able to bond 4 times, right, because it's tetravalent. And in this case, since we broke off that double bond, the carbon can now accommodate an extra bond, right? Because this carbon here is 1 2 3 bonds, this carbon 1 2 3 bonds. It's very unstable. It needs something else to fill that gap. And so what we do is that after we would have broken that double bond, we simply make bonds here on the outer regions of where the carbon to carbons double bond was, right? So that's what we're seeing here. So we just make a new bond on each of the carbons that were involved in the double bond. Once again, you make a new bond on each of the carbons where the double bond would have been, right? And this right here would be our repeating unit. This would be our monomer, right? This is our repeating unit. Know that this on its own cannot accommodate any new bonds because the double bond is present, but once you would have broken the double bond, that's what causes us to create the repeating unit and to accommodate new bonds, right? Now if you were to add multiple ethene molecules together, know that this and this, so let's say these are the 2 ethene molecules, right? And we add them together, note that this bond here would be joined to this bond, right? So this and this would join together, and that's how we get something looking like this. That's how we get our polymer, right? And usually we name them, we're going to get into this later as well, but we name polymers, we name it based on the monomer name. So for example, this is ethene. When we join thousands of ethenes together, it becomes polyethene. Remember that poly means multiple, so we're basically saying that we have multiple ethene molecules present, hence polyethene, right? So this is our polymer that we have, right? Once you would have broken the new bonds, we put them together to form a chain-like structure, our polymer. Alright, now we're going to look at the actual steps of how it is correctly done. And for this, there are some important things that you must have. Now when you're doing your addition polymerization, make sure that after you break your double bond, you attach your bonds along the side of the carbon. That's very important. So for example, step 1, we have our alkene, right? Always try to make sure that you're able to visibly see the carbon to carbon double bond. If it were a structure like this, for example, I'm just going to draw a simple structure. Now, the only bond that is able to actually break to form a new bond is the double bond. So what we're going to do is that we're going to make the structure look a little bit simple. Let it look a little bit simple. I'm just going to show you that in a second. Right, we want to make the double bond the main focus, right, without eliminating any of the old bonds. So what we're going to do is that we're going to draw our C double bond. C, that's what the main monomer is going to contain. Right, now looking at the left of this double bond, we have a CH3 group. That's a methyl group. So I'm just going to attach it, the CH3 group here. You can just attach it anywhere, exactly. So that's going to be the CH3, that's our methyl group. And note that there was a hydrogen attached to this carbon as well, so I'm just going to put the H here. On the right hand side, we have a CH3 group attached to the carbon, so I'm going to put another CH3, and the hydrogen will have been at the top. When we do this, it makes it easier for us to actually draw or join the bonds together when we break them. Note that I have it on the side, so it kind of makes it a little bit harder. So what I'm going to do is I'm going to in fact redraw this. So my double bond would be here, my hydrogen would be here, and I'm going to put the methyl group at the bottom. Right, try to do it something like this, and put the other hydrogen at the top and the methyl group at the bottom. When you do it this way, and you break the double bond, you're able to put a bond on both ends of the carbon, so it's easier for you to actually bring in or add extra monomers to this monomer right here. Right, so if you see a structure like this, once again, try to just break it down, simplify the structure using your double bond to make the double bond the main focus, and then you work your way around it. Right, let me just erase everything. I'm going to do another example before I even continue, because you need to know how to make your monomers very simple. So I have my C, let's say with a C double bond, C. Alright, so for this one here, once again, when you're making your monomer, because you need it to be very simple when you're doing your polymerization reactions. So what we're going to do is that we're going to just make the double bond portion the main subject, right? The main subject. So it's C double bond C. To the left of this carbon here, this carbon has a Cl group and a hydrogen, so I'm just going to put those back. I'm going to put the hydrogen at the top and the Cl at the bottom. On the right carbon of the double bond, this carbon has a H at the top. Right, now note that we aren't going to draw out all of this. All of this is simply CH2 CH3 if you were to do it in a condensed way. So I'm just going to put a bond here. It is CH2 CH3. And this is how you make it very simple. When you do it this way, once you would have broken the double bond, you're now able to put your additional bonds along the sides of the carbon. Right, always try to do it this way. It helps, it works. Right, if you're a bit confused about how I did this, just rewatch it again. You should get it, I hope so. All right, now for doing your polymerization reaction, your additional polymerization reaction, step one is that you break your double bond. You saw me doing it earlier. You break the double bond. That's step one. Once you break your double bond, once again the carbon is able to bond 4 times. In this case, it's bonded 3 times. So now you're able to accommodate another bond. They do it this way, but my recommendation is to draw the bond here along the side. Put your bond along the side, right? That way you know that, okay, I'm going to put my additional monomers along the side. Right, now for step two, you're going to join the monomers using single covalent bonds. Don't like what they're doing here, but what we have, I'm going to do my own little structure. So let's say we had 2 monomers, and we would have done step 1 already, right? Yes, we would have done step 1 already. So we would have already broken the double bond, and now we're at this stage where we're going to add our monomers together. Right, that's it. All right, now note that once you would have placed the additional bonds along the side, you have to put a bracket. So you're gonna put your bracket, you put a bracket and an N. When you put the bracket and an end, it's suggesting that the monomer is a repeating unit. That's what it's suggesting. Once again, when you draw your monomer, you break a double bond and you draw the monomer, right? Always put a bracket and then an end to suggest that that is your repeating unit. Continuing, doing the same thing for this one, since I would have already had my little bonds along the side, right? And then I put the N. The N means that it's a repeating unit, right? Now we need to join these together. And since we have these bonds right here open to join, the polymer that we form is simply going to be, so it's CH. The first monomer would have been CH, then another H here, H as well. And since we're joining it together, I'm going to put my bond and the bond. And I put another carbon here from the second monomer, monomer 2, right? And monomer 2 would have had 2 carbons as well. Put in my hydrogens. Another hydrogen, 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 right? And I'm going to put my curve bracket, my bond and the curve bracket. When you put the bond and the curve bracket, it's suggesting once again that it's a repeating unit. Even though this is our polymer that we form, I need to put an N here as well. Even though this is our polymer that we form, we need to put the bracket, because in reality these units, they repeat and they just continue to repeat. It doesn't end. So always put your brackets and the N when you draw your monomer and your polymer, right? Now the way we name them is based on the alkene structure, right? It's based on the alkene. So for example, this polymer here is made up of, originally it was an ethene, right? It was ethene originally, right? Even though it looks like an alkane now, remember that it was ethene originally. So the name is going to be polyethene, a polymer made up of thousands of ethene molecules or ethene monomers joined together. So the name is polyethene. All right, continuing. Now I would have done this as well. Once again, always remember to add your bracket, your curvy bracket, and your N to suggest that it's a repeating unit. Whether you're drawing the repeating unit for the monomer or you're drawing the repeating unit for the polymer structure, always put your bracket and the N. If you are drawing the original alkene that has the double bond, do not put the brackets or the N, because that, it wouldn't originally be the repeating unit. Remember the double bond, the carbons are already, they all have their bonds that they need to have, so it wouldn't be able to accommodate any extra bonds until we begin to do the polymerization reaction where the double bond breaks, right? So the original double bond, the one that has the original double bond, would not be considered, or you would not use it with the square brackets, because it's yet to be the repeating unit. All right, I'm continuing. This is just another example as well. The monomer being ethene, ethene being the monomer. Remember, you break your double bond. Once you break that, you put your bonds at the edge, your covalent bond, draw your curvy brackets and an N to suggest that it's a repeating unit, as you would have seen over here, right? This would have been your monomer. This is your monomer, and once you draw your other monomers together, that would be your polymer. This is another example. We have this is chloroethane, ethene rather. Note that they would have drawn it in a way so that we can actually just accommodate extra bonds along the side when we break the carbon to carbon double bond. Right, so once again, we break this, break that double bond, put our bonds on the edge, draw your curvy brackets and the N, making it our polymer right there. Now if this is chloroethene, then the name is going to be polychloroethene, right? That's for the naming. And polyvinyl chloride, that's actually the name that they give to this. It has many different uses, like the PVC pipes, for example, those white pipes that they used to run water through, or electrical cords through. You're gonna see the example coming up, right? So that's polyvinyl chloride. PVC is made up of polychloroethene, right? A lot of the monomers coming together to give you your PVC. Alright, now note that when we make monomers, we have to have very high temperature and pressure in the presence of a catalyst. Right, so it's not just formed just like that. We have to have a very high temperature and a high pressure along with a catalyst. I'm going to continue. If this is ethene, once again our polymer is going to be polyethene. So we're putting thousands of the monomers together to make the polyethene. But it says it has up to 50,000 of these coming together. Now these are some complicated polyalkenes. I would have given you the example of how to draw them earlier. Note that the R group represents alkyl groups. So the alkyl group would have been CH2, CH3, CH3 continuing, right? I would have given the example earlier, but just in case, right, whenever you're doing your structures, always make the double bond the main focus and you put the other part, any other R groups mean the alkyl groups attached to the double bond, this carbon to carbon double bond, just put those at the top or the bottom. It makes life easier, right? Now this R group can be X, and in chemistry when we say X, we're really talking about halogens. So the R represents alkyl groups such as methyl, ethyl, propyl, butyl, etc. But the X represents a halogen such as fluorine, chlorine, bromine, iodine, etc. Right? Now this is just an example. I am going to do another example with a halogenoalkene. So in this one here, we have ethene joining the N, once again representing repeating units. We have ethene plus ethene coming together to form polyethene. We have chloroethene plus chloroethene coming together to form polychloroethene, also called PVC. Notice where the chlorine is placed because it was originally at the bottom, right? And then we also have any other polymers. So once again, the X represents the X could be any halogen group, right, or any atom, right, and we join these together to form our polyalkene. Now I'm going to do the example of polypropene on another slide, but just so you know, polystyrene, the same styrofoam cups, that you have, right? So the X right here, instead of X, it would have actually been C6H5. So our polystyrenes, they're made up of alkene groups which has 8 carbons in total. Right, so that's your polystyrene. Yes, polystyrene, it's a polymer. Alright, I'm going to do the example of the polypropene on the next sheet. Alright, so let's say we're hypothetically asked to draw how we form polypropene. That's what we're asked to do, draw how we form polypropene. Now since it says polypropene, we are going to make the assumption, which is an incorrect assumption. We're going to make the assumption that since it's polypropene, it has to be made up of propene monomers, right? Propene monomers. And propene, how it looks, propene would have had 3 carbons. I'm just going to draw my 3 carbon structure. 1, 2, 3. And since it's an ene at the end, I know that's an alkene. It did not specify where, but I'm just going to put it on one of these carbons here. Then I fill it in with my hydrogens. Carbon can only accommodate 4 bonds, so I'm just going to make this with 3 hydrogens, right? Since it's 1, 2, 3, 4, that's full right there. Then this one would have had 1, 2, 3, 4, that's full, has enough bonds. This one, 1, 2, 3, 4, that's all right there. Okay, now once again, when you're making your monomer structure, always try to make the double bond the main focus. Always try to make the double bond the main focus. And I'm going to draw 2 of these actually. Alright, so it's going to be C double bond C. That's what it's gonna be. So I'm drawing this part right here. Now for the one on the right, it has a hydrogen at the top, one at the side. I'm going to put it at the top and the bottom so that I can accommodate any extra bonds. Right, so it's top and bottom. On the other carbon, the carbon on the left of the double bond, we're seeing a hydrogen. So I'm just going to put the hydrogen here. And we're also seeing a CH3. Right, so we have the hydrogen and we also have a CH3 attached to it. I'm just going to write my CH3. So it has 1, 2, 3 carbons, hence it is propene. Right? And I'm going to draw another one. This plus this. Now, I'm not going to put the N as yet because they're not able to really add together per se. So I'm just drawing this here. The next thing that we're going to do is that we're going to break our double bond. Right? So I'm going to break my double bonds, break it. And once we break our double bonds, we now allow our monomers to add other monomers to them, or to themselves rather. So I have my hydrogen, methyl. Oops, I don't think I can erase it very easily. Nope. Alright, would have been CH3, my bad, so it's CH3. No longer drawing the double bond because it would have broken that. And what we're doing next is that we're going to put our bond at the ends of those carbons that would have had the double bond. Put your bracket and the ends to suggest that it's a repeating unit. I'm going to do another one of these. Right, my C to C, then my H to H. And the H there. Put the bonds at the ends. Once you break your double bond, always put your bonds instantly so you don't forget. Then my bracket and my N. Now the last thing we're going to draw is the polymer. That's what we're going to draw next. The polymer is going to have all of these combined. So I'm going to draw the first structure. It would have been C, C, CH, 3, then my H, H, H here, a bond here, a bond here. For the next one, would have been CH, CH. I'll draw it a bit far apart, but you're gonna see what I'm doing. CH, the H here, the CH3 here. So I'm drawing it exactly as I see it, and then I join them together. Note that this would have had its own bonds at the end, right? And I just simply join these two to make our new covalent bond. Also, since polymers are repeating units, remember that you need to do your bracket, put your bracket and your N. So when you're drawing the polymer, always put your bracket, you add them together, put your bracket and your N. Final thing that we're going to do is that we're going to name it. Since this polymer is made up of repeating units of propene, it's going to be called polypropene. So that's the name of our polymer. Alright, I'm going to continue. Now, these are just some examples of the monomers and the polymer that they would have. So ethene would give you polyethene, chloroethene would give you polychloroethene. Notice the chlorine group, right? Then we have tetrafluoroethene. Tetra meaning there are 4 fluorine atoms found around the ethene, the double bonded C, so it's tetrafluoroethene. Then we have propene. By the way, tetrafluoroethene will give you polytetrafluoroethene, PTFE, right? Like your PTFE pots, for example. We have propene, give you polypropene, and you have styrene, which give you polystyrene, which is the polymer. All right. Now we're looking at the properties and also the uses of our polyalkenes. So polyethylene is very low density, and we use it for sandwich bags. So like your Ziploc bags, notice how thin the plastic is, right? That's what we use polyethylene for. Note that it is soft and it's also waterproof. Water is not able to go through those through the bonds of our polyethylene. Then we also have high density polyethylene, which is very hard, very tough, and it's also waterproof, such as the jugs. So the same polyethylene that you use to make the sandwich bags is the same polyethylene that we use to make the jugs, the bowls, and our plastic containers that we use in the kitchen. Right, now note that the reason for their difference in how they feel is based on how they're prepared. So one could have been prepared with a very high pressure and high temperature, while the other one could have been prepared with a low temperature and a low pressure. Now polypropene, an example is propylene. It softens at high temperatures than polyethylene. So for example, the car dashboards, food pots, fibers for carpets, those are all polypropene. Polystyrene, we know it's very rigid. It can also be transparent, and we use it for food containers. You also have the polystyrene foam, which we call styrofoam. It's very light and it's a thermal insulator. Know that these are very easy to burn, right? Because plastics, even though it says plastics, you know that alkenes are originally oils, right? That's why it's so flammable. Then we also have refrigerators for polystyrene. We use it for refrigerators, air conditioners, and protective packaging. We also have polyvinyl chloride, which is PVC, made up of polychloroethene. It's very rigid, waterproof, and can be pliable, right? So some examples of PVC. I know you've heard about PVC pipes, the rainwater goods. They use it for bottles, raincoats, shower curtains, and window frames. Those are all PVCs. These are just some actual examples. You have the polystyrene, which is styrofoam. You have your polyvinyl chloride PVC, these pipes here. Then the PTFE, which is your polytetrafluoroethylene, right? The non-stick pans, those would be your PTFE, polytetrafluoroethylene. Other examples are polyvinyl chloride PVC used for guttering. So we always put those pipes when we're trying to make gutters. And we also use polypropylene for ropes. Now note that when we're doing additional polymerization, we have to have three conditions. We have to have high pressure, high temperature, and a catalyst. Right? That's what we need to have in order to make our polymers. Features of our additional polymerization: only one product is formed, the polymer. Right? We only form the polymer. Even though it's repeating units, yes, we only form one product, which is the polymer. Note that the polymer is also made up of identical monomers. Also know that the empirical formula of the polymer and the monomer is the same. And we can look at this that we did earlier, right? So the empirical formula of this monomer right here, if we were to do the molecular formula first, it would be C1, 2, 3. So it's 3 carbons, C3H, 3, 4, 5, 6, H6. And this one here is 1, 2, 3, 4, 5, 6 carbons. C6H, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, H12. Right, and if we were to write the empirical formula, which is the simplest whole number ratio of the molecular formula, for this one it would be, of course, 3 into 3 goes 1 and 3 into 6 goes 2, so it's going to be CH2, sorry, for the empirical formula. This one, 6 into 6 goes 1 and 6 into 12 goes 2, so it's also going to be CH2. So we can therefore say that the empirical formula of the monomer and the polymer are the same. Going back, also, no atoms are lost during the process. We're only breaking bonds. We're not losing atoms. So we don't lose any atoms during the reaction, right, for polymers. Note that the properties can also be modified. When we change the monomer side groups, when we change the R groups, we change the different properties that are present, and also we can change the properties based on the type of catalyst used or the conditions. I would have mentioned earlier that you can have really high temperature and high pressure. Those conditions give you varying types of polymers. So some examples would be low density polyethene, which is soft, used in food bags like your sandwiches, your sandwich bags, your Ziploc bags. And you have high density polyethene, which is strong, used in machine parts and for jugs. Right? Now this is a summary question. What is a polymer? And explain what happens during additional polymerization. So a polymer, remember that a polymer is made up of repeating units of monomers covalently bonded together. That's our definition. Explain what happens during additional polymerization. During additional polymerization, monomers are added to each other by breaking the double bond of the alkene, right? That's just all that there is. So we break the double bond of the alkene and we attach extra bonds. We add new bonds to where the double bond was. And so now we're able to add additional monomers. That's for addition polymerization. For each of the following polymers, draw the structural formula of the monomer that is formed. So for this one, when you need to draw the monomer for the polymer, my advice is to look at where you see the repeating unit. And there's a pattern. So you have CH2, then you have CClH, then CH2, CClH. Notice that there is a repeating pattern here, right? And I would say that this is a monomer, right? And this is a monomer. And this is also a monomer. These would be our monomers. Alright, note that a good way to identify it is if you're seeing a repeating unit. Once you see the structure starts to repeat, that repeating unit would be your monomer. Even this one, for example. So we have CH2, then C triple bond N, cyanide, and an H here, then CH2, then C triple bond N, and the H. So obviously right here is just about where it starts to repeat, and I'm just gonna circle this to be my monomer. This right here would be another monomer, and this here is also another monomer right there. Now that if you were to draw these monomers, you would just simply, for example, draw just one single unit, single repeating unit, the H, the H, the Cl, the H, put your bonds on the ends, bracket, bracket, and N. That's what they're asking you to do. Draw the structural formula of the monomer. This is what they're asking you to do. Alright, give 3 examples of addition polymers and give 2 uses of each of them. We use polyethene for jugs and we use it for sandwich bags. There's also polypropene for polypropene. We use polypropene for food containers, some very thick food containers. Right, and I'm also thinking about the polyvinyl chloride or PVC pipes. And we also use PVC for shower curtains as well. Alright, so this ends the section on the addition polymerization. We link our monomers by eliminating a molecule of water or hydrogen chloride between those monomers. Now during condensation polymerization, the polymers are not the only product. So we form the polymer and we also form H2O or HCl. Right, the polymer is made from more than one different types of monomer. Right, so for example, we could have made the polymer in addition reaction, polymerization would have made it with the identical types of monomers. Right, so if we're using an alkene, it would be the same alkene repeating unit. But in condensation polymerization, we might use a carboxylic acid and we use an alcohol. So we add carboxylic acid, alcohol, then carboxylic acid and alcohol. So we're using different monomer units coming together to make the polymer. That's for condensation polymerization. Also note that the empirical formula for the polymers and the monomers are different, because once you would have eliminated water, we took out the H2O or we took out the HCl. Of course, the monomers and the polymers will not have the same empirical formula. Now, note that for this type of polymerization, we must have 2 functional groups present for the condensation to occur. So that's something that you must note. You must have 2 functional groups present for condensation to occur. Now it says condensation polymerization involves the release of usually a water molecule when 2 monomers react together to form a new bond. There are many examples of condensation polymerization and it is very common in nature. So we have each monomer must have 2 functional groups. We said that earlier, so you can have a hydroxyl group and a carboxylic group, right? 2 different functional groups, and once again we're eliminating a small molecule of water or hydrogen chloride. Note that we can also eliminate NH3 depending on the type of monomer that is present. Right, so this is how it looks. We join 2 different monomers together, the water molecule would come off, right, and then we have the repeating units between the monomers. Now these are just some examples, the examples that we're going to look at for condensation polymerization. We have the synthetic polymers, which include polyester and polyamide, and polyamide can also be natural, right? So they can be, like, for example, the proteins are some examples of polyamides, natural polyamides. And we also have polysaccharides, so like our starch, cellulose, and glycogen, which are made up of monosaccharides. First one that we're going to look at is polyamide and how we form the polyamide. Now, polyamides, they contain the amide functional group that links the repeating units together. Once again, for polyamides, it contains the amide functional group that links the repeating units together. We're going to look at how we form the amide, but this is how the amide group looks. So it's C double bond O and NH2. Right? Note that this R could also represent any methyl groups. It could have been CH3, right, or CH2CH3. So that's what the R means. Right, now if you looking at it, what 2 functional groups come to mind? Right, you see a C double bond O and you see an NH2. Right, now the C double bond O, this C double bond O is going to be coming from our carboxylic acid, Remember, your carboxylic acid is C double bond O and OH, and the NH2 is going to be coming from an amine functional group. I'm going to look at that again. Now note that the amide functional group, the amide functional group, sorry, is CONH or NHCO, depending on how it was formed. So this is what it contains. That's the amide functional group, CONH or NHCO. So to produce our amide, a carboxylic acid and an amine are reacted together. In organic reactions, acyl chlorides are usually used. So sometimes we can use acyl chlorides as well. Right, now this is how it works. Once again, this R could be represented by any alkyl groups. It could have been CH2, CH3, or CH3 alone, right? Same for this R group here. It's an extending alkyl group. Now notice that for carboxylic acid, this is our carboxylic acid functional group. The reactive part of the carboxylic acid is the COH. So this is the part that is going to come off to make the water. And for our amine, so this is amine here. Amine has the NH2, amide would have the NH2O, right? So for the amine, this is our amine functional group. One of the hydrogens are going to come off to make the water. Now we do this, when we take these off the OH and the hydrogen, note that this bond right here and this bond right here, they connect. So we eliminate the OH and we make a bond directly between the C and the N. Hence, this is how the amide link would look, a bond between the C, the carbon, and the nitrogen, right? And notice that the carbon would have had the double bond O, so we write that back here as well. And the nitrogen would have had the R group, right? That's how it looks. Now, this diagram does not illustrate the other hydrogen that is present, but this hydrogen would have still been there. I'm not seeing it on this diagram, so I would have had the hydrogen still being present here. Right, note that this is our amide link. We form the amide link between a carboxylic acid and an amine or an amine. So it's the NH2 plus our COOH. Right, we take off the OH from the carboxylic acid, that's the reactive part, and we take off one of the hydrogens from the amine. That's how we make our amide. Now, when you look at it this way, notice that R groups are attached along the ends. Alright, now when you look at these, looking at our amide linkage that we form here, notice that we have an R group here and we have another R group here. So how is it that we're going to be able to make a polymer if we have other R groups on the ends? Right, we need, in order for us to make the polymer, we need to have other functional groups besides the R groups, besides the alkyl groups attached on the end. And that's how we bring in our diacid and our diamine. So for the diacid, which is the dicarboxylic acid, we have two carboxylic acid groups attached onto our alkyl group. So we have one on the end, one on one end and one on the other end, right? And also for the diamine, we have one amine group on one end and one amine group on the other end. That way we're able to make a linkage here, right? And we can add another dicarboxylic acid right here, which would be linked to this hydrogen, right? We could also add another diamine here, which would bond with this OH here to make another amide link. So we could make an amide link right here. This is going to be our amide linkage. One is going to be right here as well. So it's just going to repeat and repeat. Note that when we're making polyamides, we have to have a dicarboxylic acid and a diamine. That's how we're going to make it. If we don't have any di means two. If we don't have any diacid or diamine, we won't be able to make the repeating linkage. So we have to have those present. Alright, the polyamide is formed by linking thousands of diamine and diacid molecules, each being connected by an amide link, and each forming a resulting water molecule. So if I had two molecules of diacid and two molecules of diamine, can you think about how many water molecules we are going to get out of that? Right, so two molecules of diacid, so we have two diacids and two diamine. How many water molecules will we form? You can leave your answer in the comment. All right, now to continue, So here we have our diacid. Once again, the R could mean any alkyl group. So I'm just going to write a little alkyl group here. CH. Same for here. CH. Note that the CH could have been even longer, because in nature they're actually quite complicated and they have a lot of different CH hydrocarbon groups in them. So we have our dicarboxylic acid, or our diacid. We're going to form our amide linkage here between the OH of the carboxylic acid. Remember that this is a reactive part of the carboxylic acid, and then from the amine we take off our hydrogen to make water. So we're condensing, we're making water. That's what's going to happen here. So between our diamine and diacid, we make one molecule of water. So if we were to add another diamine here, we would make another molecule of water. And if we were to add another diacid here, it would also make another molecule of water. Right? So therefore, if you had said 4 molecules of water from the previous question, you would have been incorrect. The correct answer is 3 molecules of water. If you have 2 diamines and 2 diacids, you would get 3 molecules of water. Now, by reacting a dicarboxylic acid with a diamine, the repeating unit form has both a carboxylic acid group and an amine group. So this is our polyamide. This is how the polyamide looks, right? It has a double bond, C double bond O, R, C double bond O, the NH, the R. Remember, the R's mean that it could be an alkyl group, then the NH. Note that this together, the repeating unit for our polyamide, has to have 2 double bond O's and 2 NH groups. That's for our polyamide. You cannot just have the carboxylic acid or just the amine. It has to have both of them joined. So this is going to be our single repeating unit, right? For our polyamide. This is our monomer. The monomer contains only one amide linkage. The polymer contains thousands of polyamide, or thousands of amide linkages. Note that when we do our dicarboxylic acid and our diamine, we make a polyamide. The linkage is called an amide linkage, right? The repeating units can go on to react with other repeating units, producing another amide link, creating a polyamide. Once again, this right here on its own is not the monomer, but when we have both combining, where we can clearly see our amide linkage here, this is our amide linkage, right? That would be our our monomer. Our monomer will contain all of this, the combination of the carboxylic acid and the combination of the amine, the diamine, right? Note that for this one would have taken off only 1 molecule of water. Once again, we also have our brackets. Our brackets are also present to suggest that it's a repeating unit. Now, natural polyamides are made from linking amino acids. So when we put carboxylic acid and amino groups, carboxylic acid and amines together, we actually naturally form what we call amino acids. Note amino, which is amine, and the acid part of it would come from the carboxylic acid. That's why it's called amino acids. So natural polyamides are made from linking amino acids together. These molecules have 1 amino functional group and 1 carboxylic acid functional group, right? That's for natural polyamides. Natural polyamides only have 1 of each functional group. So it would look something like this, for example. That's how it looks naturally. And then we would add another identical structure. So the NH, we would have the NH here. I hope you're realizing the difference from what we did before. So this is still a polyamide. However, note that from the previous polyamide, you would have had 2, it would have been a dicarboxylic acid and a diamine. But for naturally occurring polyamides, we have only 1 amine group and 1 carboxylic acid group. Right, and when we link these together, just try and complete my structure. So this is going to come and make our water, just like that. Yes, Right, now amino acids and protein. Proteins are made from amino acids. So amino acids, you only have one amine group and one carboxylic acid group. Right, each amino acid contains an R group which varies. We have 20 different types that exist in nature. And once again, condensation reaction links the amino acids and release water. Alright, so this is the example that we have. This is an amino acid. It has an amine group and an acid, carboxylic acid group. When we link two of these together, two amino acids together, right, we condense, we form water, and when it combines, we actually form what we call protein. So this is protein right here. When we have two amino acids coming together, we form protein and water. The linkage that we have here, it is still an amide linkage, or we can also call it a peptide linkage. So it's still amide linkage, the NH and the C double bond O, that's the amide linkage, but we can also call it a peptide linkage. I know you've heard about polypeptides. Yes, this is where it comes from, peptide linkage. Now note that some examples of proteins include keratin in your hair and your nails. Those are made from protein. Also collagen, which are found in the ligaments and tendons where your bones are. There's also hemoglobin, the red pigment of your blood cells. The enzymes, there are also enzymes, antibodies, and hormones, all being made up of proteins. Remember that there are 20 different types of amino acids, and when you join these different types together, you make different types of proteins that the body needs. Hence, we have different examples right here. Just to recall, for regular polyamides are made by linking a diamine and a dicarboxylic acid together to create an amide link, and we condense water. But if we're making protein is made from linking two or more amino acids together, where amino acid contains two functional groups only, which is the amine group and the carboxylic acid group. Now we're at polyester. I know you've heard of this before. Polyester in your clothes, polyester this, polyester that. Right? Now for polyesters, they're formed when a diol molecule with two OH groups. Diol means dialcohol, right? When a diol molecule with two OH groups reacts with a carboxylic acid, which is two COOH groups, right? This goes back into when you would have done esters. Remember that esters, you form esters when you link a carboxylic acid and an alcohol. And remember that esters, they have this sweet smell to them, right? Now, if we're making a polyester, which contains multiple, of course, we have to use a dicarboxylic acid and a dialcohol. But let us look, before we even go into that, let us look at the alcohol group itself and the carboxylic acid group. Right, now note that whenever we're making esters, it's a condensation reaction, because in order for us to link the alcohol and the carboxylic acid together, we have to condense water, we have to release water. So it has to be a condensation reaction. Right, so we have our alcohol here, which is the OH. We have a OH functional group, the carboxylic acid, which is the C double bond O and an OH. From the carboxylic acid, the reactive part of the carboxylic acid is the OH, and the reactive part of the alcohol is the hydrogen. That's going to combine to form H2O. Hence, the linkage is going to be between the oxygen and the carbon. That's going to be our bond, our new bond that we form, right? Hence, once again, the ester linkage is going to be made up of C double bond O and an oxygen. This is our ester linkage here. That's how you're able to identify esters. They have COO. So carboxylic acid would have COOH. Esters have COO. Note that this oxygen is linked to another CH group. This would have been our ethyl group. And for the C double bond O, that's linked to a CH3 group. Alright, now continuing, when we're making polyesters, once again, we have to have a dialcohol and a dicarboxylic acid. Note that if we just had these, the hydrogens themselves, they're a bit unreactive. How are we going to make the polyester if we just have hydrogens on the end, right? So that's how our dialcohol and the dicarboxylic acid comes in. So polyesters, they contain an ester group that links repeating units together. This is our ester group, the COO, that's the ester functional group. To produce an ester, carboxylic acid and an alcohol are reacted together in the presence of an acid, right? example phosphoric acid, that's an example. This forms an ester link but not a polymer, as the product is not able to form more ester linkages, as I would have said earlier. Hence the reason for using the dialcohol and the dicarboxylic acid. So in the dicarboxylic acid, we're going to use our reactive part of the carboxylic acid, the OH, along with the hydrogen from the alcohol. We do our condensation reaction, hence we make an ester linkage between the oxygen and the carbon, right? Notice the product, we have another carboxylic group on one end and we have the OH group on the other end. Now because we have these reactive sites present, we're now able to actually do a polyester linkage. We're able to make a polyester. So on this end that has the carboxylic acid, can you think about which polymer or which monomer I'm going to put here so that I can do a condensation reaction, especially for polyester? Right, now if you would have answered that the answer would have been alcohol, a diol, then you would have been correct. So we could have used back the same diol that has an OH group right here. The carboxylic acid won't react with the carboxylic acid. It has to be the carboxylic acid being attached to the alcohol so that we can make the ester. Alright, so from the alcohol, the OH from the alcohol reacting with the the OH from the carboxylic acid reacting with the H from the alcohol. And for the alcohol end, we have to put our carboxylic acid functional group. Well, there's something attached to this as well. Right, the OH being the reactive part, and then react with the hydrogen to form another molecule of water. So when it's diol or dicarboxylic acid, we're able to create polymers. That's what we're able to do. Now this is going to be our polyester. So by reacting a dicarboxylic acid with a diol, the repeating unit formed has both a carboxylic acid group and an alcohol group. Right, this is how it looks. This is our repeating unit. Now the double bond O, and our O from the alcohol, the diol, and the other O from the diol. There should be yes, this is actually it because what this bond is suggesting is that there is there could be another C double bond O here, and then the R, then the C double bond O. So that's from the carboxylic acid. And for the alcohol, so after we would have added our carboxylic acid, we have to repeat it with an alcohol. So notice that it's going to alternate. So it's carboxylic acid, the dicarboxylic acid, then the diol, then the dicarboxylic acid, then the diol. Right, so it's just going to continue and continue. I'm at the diol, so of course the other repeating unit would have been our dicarboxylic acid, and it continues. Likewise for the left hand side, if it's a diol here, I'm going to put this is a dicarboxylic acid, so it would have been a diol being attached, and it just continues and continues and continues. Note that this is one monomer unit. This right here is one monomer unit. This right here is another monomer unit. Note that the monomer for polyesters contain both the carboxylic and the alcohol functional group. So that's a good way for you to look out for it. It doesn't contain only the carboxylic acid or only the alcohol. It has to contain both. That's what makes up the monomer. So some examples of polyesters, we have the PET bottles, or plastic bottles. That's polyester. The same polyester that you have in your clothing is the same polyester that you drink from. However, based on the type of pressure and temperature that these are made under, we're going to get different types, different textures from our polyester products. We also have polyester chips. We have some flakes. We use it for spinning, weaving, fabrics, etc. Yes. Other uses of polyesters, we would have already mentioned the clothing and the fabrics, the PET, the packaging of plastic bottles and containers, and engineering plastics like car parts, films, and ropes. They're very durable, lightweight, and resistant to shrinking and stretching. So just think about it. Polyesters, we use it for fabrics, and we use it for packaging. So packaging of including plastic bottles and containers. Right. An example of polyester is polyethylene terephthalate. also known as PET, or by brand names such as terylene or Dacron. So the polyethylene terephthalate is formed when a diacid in which X has the formula C6H4. So X right here would have been C6H4, which is 6 carbons and 4 hydrogens, and the diol in which the Y is C2H4. That's how we make our polyethylene terephthalate. You can look up how that looks, but it's mainly found in fabrics. Just to do a quick recap before I move on, just remember that polyesters, they are made up of a dicarboxylic acid group and a dialcohol group. The linkage between both is what we call an ester linkage, and whenever you add both together, you form it's a condensation reaction where water comes off. So you form an ester linkage and you form water. Now the last one is polysaccharides, and polysaccharides, they are natural polymers formed by linking monosaccharides together. So some examples of monosaccharides are glucose, fructose, and galactose, which all share a similar molecular formula of C6H12O6. And this is how our glucose looks. So it's C6, 1, 2, 3, 4, 5, 6, H12O6. This is how glucose looks. Let's take a second to digest the structure. Note that each carbon has an OH along with an H. Because of this, we're able to do a little condensation. This part being the reactive part of our glucose molecule. So each carbon will have a CH and an OH. Notice that they're alternating. They're all alternating. Yes, and this carbon here would have had a CH2OH group attached to it, along with a COC group attached to it. Now starch is formed when glucose undergoes condensation polymerization. Right, so this is glucose right here. The X represents a repeating alkyl group. Right, now from this, note that one of the glucose structures would give us our OH group, not the OH group, but the OH itself. And even if it's the identical glucose structure, we're going to get the hydrogen from the other glucose molecule, and that's how we make water. So we join these together and we make water. So this is a prime example of what really happens. We have this would have been glucose right here, would have had the OH right here, would have also had the OH. Right, and note that when we're making water, the OH has to come from one and the hydrogen comes from the other. When we do that linkage, we have an oxygen remaining. Right, this oxygen is what we see right here. Now this linkage, it's not an ester linkage, but that ester is C double bond O O. Right, this linkage here is COC, and we call it an ether linkage. Right, so the ether linkage is what links the monomers together. That's the linkage. Now other examples besides the starch that we could make, we could also make cellulose that we find in sugarcane and trees, and we could also make glycogen, similar to what we use for like fats and oils, etc. Glycogen. Alright, continuing. I hope that was pretty straightforward. Now know that once again that if it's glucose, if it's a repeating molecule of glucose, the OH comes from one, the hydrogen comes from the other molecule. The linkage between both is a COC linkage called the ether linkage. Now that's a quick summary. When we have diacid plus diamine, this is a dicarboxylic acid plus the diamine, we make a polyamide. Right, that's what we make. We make a polyamide, which is joined by an amide linkage. Right, the next one, if we have two amino acids coming together, remember that this is another type of polyamides where we don't have a dicarboxylic acid or a diamine. So when we have two amino acids coming together, we create a protein which is linked by a peptide linkage or an amide linkage. Same thing. If we have a diol and a diacid, we create a polyester, right, which is joined by the ester linkage. If we have a monosaccharide and another monosaccharide, we create a polysaccharide, which is joined by the ether linkage, which is COC. So you can take this down as a little note. It helps you to remember what is going to be formed and the type of linkage that is present. So some uses of condensation polymers, we have for polyester PET, terylene or Dacron, polyethylene terephthalate, So we use it for clothing, for outdoors, for towels, boat sails, carpets, soft drinks. We also use it for packaging of, like, for example, the water bottles and food containers. For polyamide, we have nylon. Nylon is a good example of polyamide. We use it for fishing lines, seat belts, carpets, and clothing, and nylon stockings and some other active wear. Another polyamide, so this is the synthetic one, this is the natural one, which is protein, which we use in hair, nails, keratin, collagen, etc. Hormones, enzymes, antibodies, hemoglobin, those are all examples of protein. There's also polysaccharides, which for example, starch. We use starch for making energy during respiration in living organisms after first being digested to glucose. These are stored as a food reserve in living organisms. Another example of polysaccharides includes cellulose, which are used to build cell walls of plant cells. That's cellulose. Some key features of condensation polymerization. So two products are formed. The polymer, a small monomer of H2O. That's a key feature. Remember that for condensation polymerization, we form a polymer and we also form the water molecule or the hydrogen chloride or the NH3 group. Note that the polymer formed and the monomer used do not have the same empirical formula. And note that more than one types of monomers are often used for condensation polymerization. So if you were to ask to differentiate between addition polymerization and condensation polymerization, you could say that for addition polymerization, it involves using identical monomers that have double bonds. But for condensation polymerization, it involves using different monomers with different functional groups, and usually the polymer and the water molecule is formed when both monomers are joined together. So for the environmental impact of synthetic polymers, these are also called plastics. Synthetic polymers are plastics and have harmful effects on the environment. So the same polymers that are in the body that are quite useful, similar names, let me not say the same, but they have similar names, is the same polymers, made of the same functional group. Let me say that. We have the same functional group that are very harmful to the environment. So plastics, during the manufacturing of plastics, toxic chemicals are released. You might release some carbon dioxide, some methane gas into the environment. These are also released when the plastics are in use or being disposed of. They are persistent and remain in the environment for thousands of years. Number two, most plastics are non-biodegradable, meaning that they take a while to they're not able to be degraded. Basically, they build up in the environment and lead to land and water pollution. They are harmful to aquatic organisms, often leading to their death by suffocation or ingestion. So look at this turtle here, in distress because of our plastics. Plastics produce dense smoke and poisonous gas when burnt. This leads to air pollution and causes health problems such as asthma, immune system damage, cancer, damage to the nervous and reproductive system. So the compounds in plastics can also alter the sperm epigenome. Compounds in plastics can alter the sperm epigenome, leading to heritable changes in the offspring that are associated with adverse outcomes such as obesity and reproductive organ disease. So what that's saying is that because of the smoke and the pollution from plastic, it can cause damage to the human reproductive system, which can cause genetic disorders. So that's why we have obesity being like considered as a genetic disorder, because of plastic, the effect of burning plastic in the environment. Plastics are flammable and pose fire hazards, right? And it's really flammable. When you think about it, it's flammable because of the compounds that it is made of, right? It has some form of methane, or let me not say methane, but it has a CH3 group, which is quite the hydrocarbon group, which is quite flammable, right? So it poses as a fire hazard. These plastics are made from petroleum, which is non-renewable and depletes petroleum worldwide. So plastics are in fact made from petroleum. Now I find this quite interesting because our bodies themselves actually have some form of petroleum in them. That's why we're able to create our own proteins. Yes. No, this is saying activity. This is from a past paper question, and we're just about down to the end of the video. So for the past paper question, first one, polymerization is an important industrial process used in the manufacturing of many useful materials. Define polymer. A polymer is a large molecule made up of many small repeating units called monomers joined together in a chain. So example, plastic, starch, proteins. Note that this is a 1 mark question, so you just give your simple answer. A polymer is a large molecule or a large macromolecule made up of small repeating units of monomers joined together. Simple, 1 mark. Distinguish between addition polymerization and condensation polymerization. Now for addition polymerization, monomers with double bonds, usually alkenes, join together without losing any atoms. You don't lose any atoms at all. Example, ethene joins together to form polyethene. But for condensation polymerization, monomers join together and a small molecule such as water or HCl is lost during the process. For example, when we join amino acids together, we form protein and water is lost. Now this is another question. We have this here. Figure 2 illustrates the formation of a polymer. We have this is C double bond OOH, C double bond OOH. This has to be a dicarboxylic acid. I'm just gonna put a diacid here. So it's a diacid, and we have NH2, that is a diamine. When we link both together, we create this monomer right here. That's our monomer. So it's a diamine and a diacid. When we do diamine and diacid, we create a polyamide. That's what we create. So state the type of polymerization represented in the video. The type of polymerization would be either addition or condensation. The fact that we're making water suggests that it has to be condensation polymerization. And it says give an explanation for your answer. As I said, a water molecule is released when both polymers or when both monomers are joined together, right? Hence it has to be a condensation polymerization. And also the fact that we have 2 functional groups attached on the ends also suggests that it's condensation polymerization. Identify one use of each of the following types of polymers. So polyester, simple, food containers, plastic bottles. We also use polyester for clothing, right? Polyalkene, those are found in plastic bags and some plastic containers like your Ziploc bags, and we also use it for packaging and for toys. That's for polyalkene. You get 1 mark each. These are some multiple choice. I have 10 and we're going to go through all 10. Which of the following is a condensation polymer? Note that these all have double bonds. The fact that we have some double bonds here suggests that these are all addition polymerization. Right, always think about it. If it's an alkene, it has to be addition polymerization. Nylon would be condensation polymerization. I believe nylon is a polyamide. Let us go back to see if I'm correct. Yep, nylon is a polyamide. Yes, so it has to be condensation polymerization. The monomer of starch. Starch is made up of glucose. Yes, that's the correct answer. Thousands of glucose monomers combine to make starch. What is lost during condensation polymerization? Water molecule is lost. What type of linkage is found in polyesters? It's an ester linkage. Amide linkage is found in polyamides. This would be a no for any of the polymers. Ether linkage is found. Right, so ether linkages are found between our polysaccharides. That's for ether linkage. It's a COC, and the ester is the COOC. That's our ester. Amide would have been NHOC. That's amide. Alright, so it says for polyesters, it's an ester linkage. Which of the following contains an amide linkage? Amide would have to be protein. Cellulose would have been a polysaccharide. So that would have been an ether linkage. This is ether linkage here, because it's made from polysaccharides. So to find polymers are biodegradable, it has to be starch. And once you see the enes, alkenes, those are all plastics. The plastic containers, your ropes, all of these are plastics. Starch, on the other hand, it's biodegradable. It's made naturally, so it has to be biodegradable. Number 7, the repeating unit CCCC indicates an addition polymer. Yes. If it were condensation, you would see functional groups attached. So like you probably see an amine functional group or a carboxylic acid, that would make it a condensation polymerization. Which other one is not a product of condensation polymerization? So not a product, this of course, the ethene. Polyethenes, those are addition polymerization. The linkage formed between glucose molecules in starch is called an ether linkage, that's correct. Which other one is a natural polymer? Cellulose is a natural polymer. And we link with the glucose, fructose, galactose, you make cellulose. And I'm going to leave the video here. You may take a picture of this and attempt these questions. If you have any questions, you may type it in the comment section and I will respond when I'm able to. So this is one and this is the other. Now that's the end of Miss Wallace Teaches Chemistry. I hope you learned something from this video between addition polymerization and condensation polymerization. That's it with Miss Wallace Teaches